So our next speaker is Katharina Dobs from MIT, who will talk about that familiarity affects early perceptual stages of phase processing.
All right. Today I will talk about how familiarity affects early perceptual stages of phase processing. And this is work by Leyla, Dimitrios, and Nancy too. So when we see phases, we immediately extract various different dimensions from them. So for example, if I would ask you to sort these phase images by gender, you could do this without any effort and without doing any mistakes. So you would sort them into male and female phases. I could also ask you to sort these phases into images that look familiar to you versus images that are unfamiliar to you, or phases that are unfamiliar to you. So that might look like something like that. How about if I ask you to sort these images by identity? So in the case that they're familiar phases, you might have noticed that, oh yeah, these two images actually belong to Daniel Radcliffe. And then maybe you could also tell me that these two images belong to Meryl Streep, and it would be fairly easy. However, extensive research has actually shown that the same task for unfamiliar faces is much harder. So it will be very difficult for me to tell me that these two images belong to the same person if the person is unfamiliar to you. And I just want to note here that when I talk about identity in this talk, I mean the fact that face images of the same person are more similar to each other than to other face images, whereas familiarity means that all the face images that are familiar to you are more similar to each other than to unfamiliar face images. So an understanding of face perception will ultimately entail an understanding of the computations of these processes. And we know from monkey and human studies that object and face perception proceeds various stages of transformations, and also successful artificial models, such as convolutional neural networks, contain a feed-forward cascade of transformations. So it seems that a key property of any complex computation, be it biological or artificial, is that it proceeds various stages and hence unfolds over time. So here, we actually want to unfold phase processing over time and determine which information is extracted when and how is the system affected by experience. So in particular, we want to ask two main questions. First, when are phase dimensions such as gender, identity, and familiarity extracted during phase processing? So you could imagine that when you see a phase, the first thing that comes up is the gender of the phase. A bit later, you're extracting the identity. And then after some time, you also extract the familiarity of the phase and maybe some memory associated with that person and so on. You could also imagine that all these things basically happen at the same time and they will be processed more interdependently. They could be processed late during the processing. They could also be extracted very early during processing. So that's one thing we want to find out. The second question then, given the demonstration I just showed you at the beginning, is how does the fact that our phase perception seems to be so much more robust when we have familiar faces than when we look at unfamiliar faces, how does that affect our processing? So how does familiarity affect the processing of identity and gender? Can we find a neural signature for that effect? So to find out, we're using magnetoencephalography, so MEG, that will provide us with a high temporal resolution on a millisecond scale. And we show our subjects lots of face images. And so they would see face images of 16 different identities, and I'm exemplarily showing you 8 of these here. And we would choose these identities such that they were different gender, so half of them were male and half of them were female. And we also chose them such that half of them were familiar to the subjects and the other half is unfamiliar to the subjects. So the one half were US actors and the other half were actually German actors. So in case there are German people here, they might look familiar to you. And then we selected 5 different images for each of these identities that would bring a lot of variation in the images, like in lighting, pose, eye gaze, and hairstyle, and so on. So in total, these were 80 images. They would then present in the MEG to our subjects. And we would ask them to perform a one-back image task. So they would have to press a button whenever the same image is repeated twice in a row. So we would intentionally not direct their attention to identity, gender, or any of these dimensions. It's really on the image. And then throughout the experiment, they would see 28 repetitions of each of these stimuli. And we would then analyze the data. So we'd first run a principal component analysis to reduce the MEG sensor data to principal component patterns. So we would get a pattern of a vector of patterns for each of our stimuli, for each trial, and each millisecond when the image is on or when the image is presented. And what we do then is we would select one time point, so let's say the first millisecond, and extract all the trials and then average them into 5 groups. So we'd run a 5-fold cross-validation running a support vector machine now, and that should classify 2 conditions. And we would do this for every pair. We do this 100 times, and the average decoding accuracy would then tell us something about how dissimilar these 2 conditions are based on our MEG data. And we would do then the same thing then again for all the other milliseconds when the image is on. So at the end, what we get is a decoding matrix that is resolved over time for each millisecond, and that tells us something about how dissimilar these phase images are represented. So I will refer to this as representational dissimilarity matrix, or RDM, throughout the talk. We then conduct representational similarity analysis to find out which of these phase dimensions that we put in the stimuli can explain our data. So when we take our RDM, the AD images, we can actually define models that represent the dimensions in the data. So we'd first define a familiarity model that is 1 when it's between unfamiliar and familiar faces, and it would be 0 when it's within familiar or unfamiliar faces. Can do the same thing for gender, so that would be our gender model representing the gender information. And then we would also do the same thing for identity, so that model is always 1 when it's between different identities and 0 when it's the same identity. And then we would correlate these models with our MEG RDMs. And importantly, what we would do is for every model, when we correlate it with our MEG RDMs, we would partial out all the other models. So for example, for identity, we would correlate the identity model, but then partial out the gender and familiarity model. And that's just because you can imagine that when you look at identity differences, gender differences might also contribute to that. So we want to basically look at the contribution of identity invariant of gender differences or differences in familiarity. However, you could still imagine that there are low-level stimulus properties that also contribute to these differences. So we would control for low-level stimulus properties by using a convolutional neural network. And these networks, as we've heard a lot before, actually work really well. In particular, the early layers of these networks are good models of the early visual system, like V1 in our system. So and this network here in particular, VGG face, has been trained on millions of face images. So we would present this network with our stimuli and then extract the features from the second convolutional layer, and what we would then get is a vector of features from that layer for each of our stimuli, and we can again calculate the dissimilarity by using 1 minus correlation as a distance measure, and that would give us a point of how dissimilar in our RDM, how dissimilar these images are based on the low-level features. And then this RDM, we would partial out from all the analysis. So everything I'm presenting you today will partial out the low-level feature RDM based on that analysis too. So to come to the first question, which phase dimensions are extracted when? Well, the first thing we want to know is at what point can our MEG data, at what point can we discriminate different images from each other? So that's not about faces in particular. That will be the same if I present object images or whatever. We want to know at what point does the fact that these images are presented, when can we discriminate them based on the image data? And what we do to do that is we take the RDM, and which is full of decoding accuracies, and we just take the average of these decoding accuracies and look at them over time. And basically the point at when they become significant tells you something at what point you can discriminate the images on the MEG data. And what we see is that yeah, we can do this. We can do this with up to 70%. And when you look at when this time point is significant, you can, from the lower bar in the plot here, that's when it's significant, we can extract the onset of that image decoding, and that is around 55 milliseconds. So that tells us something about, okay, at that point, we can discriminate the early visual properties of our images. So how do our models now perform? So what we would do is we correlate the gender model with our MEG RDMs, partial out all the other models, partial out the low-level stimulus features, and now instead of decoding accuracy at the y-axis, you'll actually see the partial Spearman correlation. So we want to see how that works, and we actually find that the gender model correlates with our MEG RDMs. So we find that there is gender information in the MEG data, and we can now again extract the onset of that correlation, and what we find is that it starts around 75 milliseconds, and it's significantly later than the image decoding that we've shown before. Can do the same thing for the identity model. So now we correlate the identity model with our MEG RDMs, partial out the other models. And we again find that there is identity information. So the identity model correlates, and when we extract the onset, we see that it's actually later than image decoding, but it's also significantly later than our gender model. So which is suggesting that we would first extract, that you can first extract information about the gender and then later information about the identity. How about our familiarity model? So that model suggests that at some point, or that model represents that at some point, all the familiar faces become closer to each other versus all the unfamiliar faces. So it might represent something about you associate memories with familiar or unfamiliar faces. So it seems like a bit like a higher conceptual representation. When we correlate that model, we actually find a correlation where the onset is much later than for these perceptual models that I've shown you before. So when we extract the onset, and I'll need to zoom out a little here, we actually see that that starts around 320 milliseconds after you've seen the image of a face. And that is obviously significantly later than all the other onsets I've shown you before. So to come to the first question, when are face dimensions such as gender, identity, and familiarity extracted during face processing? Well, when we see a face, it takes about 55 milliseconds that visual input arrives in our visual system. We can discriminate that. It's like the V1 onset. 20 milliseconds later, we can discriminate the first features that represent gender. At around 95 milliseconds, we represent features that allow us to discriminate different identities from each other. And then much later during the processing, at around 320 milliseconds, we associate something like the familiarity with that image. That's when we extract this. So we first extract gender and identity, and then later familiarity. So to come back to the demonstration at the beginning that I showed you, where we've seen that face processing, or it has been shown a lot, that face processing seems to be more robust for familiar than for unfamiliar faces. Now we wanted to see, okay, how does familiarity affect these dimensions like gender and identity? And in order to find out, what we did is we basically separated the analysis that I've shown you before, but now separated them for only familiar faces or only unfamiliar faces. So we would basically restrict our analysis to 1/4 of the data, so we have much less power here, to understand how the process and the analysis that I've showed you before, how they differ when we only restrict ourselves to these two types of face images. So we'll first do this for gender, correlate the gender model, and now only for familiar faces. And what we see is that there's still gender information when we restrict ourselves to familiar faces. Now we do the same thing for unfamiliar faces, and we find that there's actually a zero correlation for unfamiliar faces, so gender seems to be represented less well in unfamiliar faces. And when we take the difference, so we would just subtract these time courses for every subject and average that, we find actually that this difference is significantly significant, so that's shown at the black bar at the bottom. And now we want to do the same thing for identity. So how is identity affected by the fact that you are familiar with the face or not? So when we look at familiar faces, there's still identity information. We can still discriminate identities for familiar faces. However, when we do the same thing for unfamiliar faces, we no longer can discriminate identities. And that difference is again significant. So what that shows us is, one, that familiar faces are, like, the familiarity with the face enhances the processing of gender and identity. But surprisingly, what we also find is that when we look at the onset of when this enhancement happens, it's actually very early. So this onset is significant when you look. It basically overlaps with the time point when we first extract these dimensions. And that was, a bit surprising to us. So to summarize, how does familiarity affect the processing of these dimensions? Well, we find that when a face is familiar, we can well discriminate the gender, and when the face is unfamiliar, we can actually do it a little less well. And when we look at the identity, it's a similar pattern. We can well discriminate identities of familiar faces, and when they're unfamiliar, we can no longer extract them, at least based on our data, but that goes well with these behavioral findings that suggest that our face perception is much worse when the faces are unfamiliar. We can worse match these images for unfamiliar identities. And when we look at the time point of when this enhancement with familiarity happens, we find that it actually happens early at the same time point when we extract these dimensions, which might suggest that it's actually more a bottom-up tuning than a top-down effect that is affecting the feed-forward processing stages. So familiarity enhances these dimensions at a very early stage. And then we're adding a third question, which is, are these results meaningful to behavior? And that's just basically because we're looking at multivariate pattern analysis here. It's a very sensitive method, and we have small effects. So it's important to ask, are these effects, should we care about these results, and are they actually relevant to behavior? So what we did is we asked our subjects to perform a multi-arrangement task. So we showed them the same 80 stimuli that we showed them in the experiment. 14 of our 16 subjects participated in that. And so they were asked to sort these images by similarity on a 2-day display. So that could, for example, look like that, but they would do subsequence trials with smaller subsets. And the distance between these images and in this 2D arrangement would then tell you something about how similar they perceive these images. So at the end of that method, you would get an output, which is an RDM that's representing the dissimilarity between our stimuli, but now based on the behavior of our subjects. And we could then correlate this with the MEG RDMs that we get from all of our subjects using Spearman correlation, and we could again do this over time, so we would do this with the MEG RDMs for every millisecond. And when we do this, what we see is that we actually find a correlation between our behavior and our MEG RDMs. And the time point that correlation is significant overlaps with the results and the effects that I've shown you before. So we actually find that our results, these results that I'm showing you here, are behaviorally relevant. To conclude, we find that the extraction of face dimensions follows a coarse-to-fine time course, such as gender develops earlier than identity information, and familiarity comes in much later. At the same time, we find that familiarity enhances face processing at a very early stage. And that seems to suggest that there might be some early detectors for familiar face features in the visual system. And there's other behavioral studies, and there's also neurophysiological data who might suggest how that could be implemented. So there's more future work to be done here, but it seems like an interesting thing to investigate further. We also find that our MEG face representations are relevant to behavior, and that's satisfying the need to relate multivariate brain patterns to human behavior. And now you might also wonder, since we're at CCN and we've seen a lot about this, can models of the visual system explain our results? Well, we're currently looking at that, so stay tuned. And by that, I'd like to thank Nancy, my supervisor, Leyla, Dimitrios, the collaborators, and my lab, and you for your attention. Thank you very much.
We can take a few questions.
So thanks for the fascinating talk. So many questions, I guess I'll just have to pick one. Your MEG data, so could you say a little bit more about, did you use all of the data? Because I just wonder if maybe the patterns you're seeing might differ, say, in the frontal cortex versus temporal occipital cortex, for example.
Right. Yeah, so this is based on all the MEG sensors. Yeah, so we were basically interested in, when we take all the power from the brain, when can we first extract these dimensions? But yeah, that's right. If we would restrict this to partial sensors or do some sort of source localization, we would probably find different, they vary in the time course, yeah, I agree, but we haven't looked at that, yeah. Thank you.
Hey, I'm curious for the demographics data that you just looked at gender, and I'm curious if you can also look at age or racial ethnic background, like how did you select this?
Very good question. Yeah, you might have noticed that the identities varied in age too. So we had these identities that like some were younger and some were older, and I wish I had a slide for that, but we had a problem with our server the last day, so I had no access to the data. But age and gender generally showed a very similar thing. So age also comes before identity, and it's at the same time point as gender. That's the other dimension we looked at. We wondered about other dimensions like race and so on, but they bring like huge low-level confounds usually with them, so that's why we, for now, restricted ourselves on that, yeah.
And do you think for gender there are no low-level feature differences that can?
Oh yeah, but that was just, I mean, that's what we took care of with partialing out the low-level features, yeah. But it's also, it was really hard to find these dimensions and at the same time find faces that are familiar to everyone and then find 8 matches that are unfamiliar to everyone. It's actually much harder than one would think to find these identities that most of the people know and that vary then in these dimensions. So we were kind of the limit of, yeah, what we could like assimilate, but yeah.
We'll reconvene at 1 p.m. for our next keynote speaker. Last round of applause for all our speakers.